Hello and welcome to week 3. We're going to jump right into more computer control, and this time we're really going to stick to the output side of the circuits. Last week we were dealing with diodes, and before that we've dealt with resistors, and so this week we'll be really focusing towards how computers control the output side of their circuits, and that's through transistors. So inside of our computers or our modules, we're going to get inputs coming in from sensors like switches, position sensors, speed sensors, light, temperature, all that good stuff. The computer, based off of its internal structure, just the way that it's physically made as far as the circuits go, its programming, and its memory, it will decide on what output makes sense or the environment that it's found itself in. If I open up the door on my car and I have selected that I don't want the internal lights to come on, the interior lights, then the vehicle may turn on a few of the lights. Like I know that the ones in my footwell still come on, but the bright light overhead doesn't come on, so that I don't have to squint my eyes at nighttime and lose my night vision and stuff like that. So that's how it will decide what outputs to control, and the way it controls those outputs for the most part are with transistors. And just the look between our electrical circuit at the top and electronic circuit at the bottom. We dealt with this stuff last week, so I'm really not going to spend a whole lot of time on it. It's just to help jog our memory. The circuit board itself, there are transistors that are super tiny built into these dual inline pin chips. And here's a couple transistors right on the board themselves. Anything with a Q next to it tends to be a transistor, I found. There's a central processing unit, so this is the major brain of the vehicle. This is doing a lot of the work, and a lot of the information that it's making decisions from are from this PROM, programmable read-only memory. So this is how we can make adjustments to the way that this board is going to react to certain inputs and the way the outputs will be controlled. Just like our diodes last week, our transistors are still semiconductors, and they're made of the exact same materials. We're going to start with silicon that has this beautiful lattice and is a very, very good insulator and very, very stable. And we're going to dope it first with phosphorus, which is going to create our N-type material. And then second, we're going to dope it with boron and make P-type material. And there's our diode right there. P-type on the positive side, N-type on the negative side, which would be forward biased and with the right amount of voltage, which we have figured out is on a diode could be as low as 0.6 of a volt, or on an LED all the way up to 2.5, 2 3/4 of a volt. If we get enough pressure, we'll be able to push current across that junction, otherwise known as a diffusion barrier, and then current will continue to flow at that point, which is pretty interesting. And the current that flows is pretty much without limit. The rest of the circuit needs to limit that current flow for us. So when we get to transistors, you can see that there's a lot of similarity there. We still have P-type and N-type, and we still have symbols on here that look like a diode, right? The arrow points in the direction that current will be allowed to flow. And this is conventional theory current, so the stuff that we're used to dealing with. And if you take your meter and you touch the red meter lead on the base and the black meter lead on the emitter of this NPN style transistor, it would show us what the bias voltage is required to flow current through that, which in most of these is about 0.6 of a volt, just like a regular diode would be. The thing that's cool about this, though, is I'm going to put like 5 milliamps, 0.005 amps here at 0.6 volts, and that will allow 100 times more amperage, so that would allow 500 or half of an amp of current flow across my collector and my emitter. I have an image that will help us kind of get an idea of the siphoning that happens. As far as electrically, the distance between these 2 points is enough to act like an open switch. When I start flowing current through the base, now all of a sudden the distance between the two isn't as great, and this actually starts to become saturated, meaning currents flowing through it, electrons are starting to do its thing, and it allows this larger current then to overcome that barrier and start flowing as well. All right, so it's like we would have like a forward biased diode here, forward biased, and that allows these two N-type materials basically just to bypass the P material at that point. And there's a video that is referenced at the beginning of the lab that does a really, really nice job visualizing this. And it's a little bit dry as far as it sounds like a computer's talking to you, but what's happening right now? Basically, I'm talking to a computer and a computer's talking to you, so not a big deal. On a PNP style transistor, well then current's going to need to flow this way. So here I was putting voltage here, flowing current towards my ground. Well, in this case, PN, remember positive side of the circuit, negative side of the circuit. Well, voltage is coming in here all the time, and to allow it to flow from the emitter to the collector, in this case, it's just backwards from our NPN style. Well, then I need to supply ground at the base, which would allow this little bit of current to start to flow, and then the larger amount of current to flow after the fact. So that arrow is going to really help us identify in schematics what type of diode or transistor we're working with. So if we have a low current flowing, then the high current can flow. And we're talking magnitudes of 100 here. It's huge. This is a nice German diagram I found. I looked for all kinds of GIFs that would allow us to kind of understand what's going on, and I think this does a pretty nice job. It definitely isn't in the physical world. It doesn't make sense as to what's happening, but to wrap your brain around the whole circuit, this is definitely it. This little bit of current opens up the pathway for my large current to flow, which is exactly what's happening here. So in this, here's my NPN transistor. You can see because it's NPN, and the N materials need to be on the negative side of the circuit, this is going to be a ground side switched transistor. It's always, well, the transistor acts as a ground side switch for the rest of the circuit. It is actuated with power, and this one needs 10 milliamps to open, so that would be 0.01 amps, very, very low, and this is allowing 250 milliamps to flow through the circuit, and that amperage is limited merely by this resistor right there. So in this case, we're amplifying, because transistors are often referred to as amplification devices. We're amplifying a 0.01, let's try that again. We're amplifying a 0.01 amp flow to a 0.25 amp flow. So 25 times more current is flowing across my collector and emitter as what it takes to actually turn that thing on and create a pathway to ground. We can also use these to create gates. So this is called an AND gate because I would need this transistor turned on and this transistor turned on. And what that actually means is, let's say I have my headlights turned on to auto. I would need a signal showing that my headlights are on auto because I have it on that selection on the switch of the dashboard. So this has been turned on, and I would need my light sensor, maybe my photoresistor or maybe a photodiode, to then turn on when I had a dark enough atmosphere for my lights to turn on, right? Because we're not going to just turn on the headlights all the time. Going to put drag on the charging system, which drags on the engine, which reduces fuel economy, and manufacturers are trying to produce as much fuel economy as physically possible. We can use a Darlington pair, and Darlington, just like all these other things, is the name of the scientist that figured this out, and this is a pretty large amplification circuit. So in this case, I could have 5 milliamps turning this transistor on. That allows 500 milliamps to flow through it. That then could allow 5 amps to flow. It could allow 10 amps to flow, depending on how robust this transistor is and how much resistance is on this circuit, limiting the large current flow's ability to flow. H-gate operation. Well, we're dealing with DC motors this week, and H-gates are the way that a lot of computers can control the polarity of our motor. So I've got two PNP style transistors on the top, PNP, so they're on the positive side, I've got 2 NPN, and you can see that their symbols are slightly different. These are on the ground side. If I want my motor, let's say I want it to roll this way, which would be, let's call it up. I'm rolling my window up. Then I would apply a ground to both of my A bases, these PMP, and that would allow current to flow from here, down through this, and my motor would spin this way. If I want it then to roll back down because I like farted or it's hot inside the car or something like that, then I would apply a ground to the B and a positive to the B. Sorry, I misspoke on the first one, but you get the point. And current will flow the opposite direction, counterclockwise in that case, and my window would roll back down again for me so I could air it out. And that's what it looks like if we actually saw one wired up in a schematic. But oftentimes, this is all the schematic will show us is, don't worry about what's inside the box. Pay no attention to the man behind the curtain. It's all smoke and mirrors. All they want you to do is, does the window roll up and down? No. I'm going to check to see if it rolls up and down, right? Verify customer concern. Still doesn't roll up and down. Is this computer getting the input that it needs to know to roll the window up and down? Well, that depends on the circuit. Maybe it just gets 12 volts on one wire coming into it. Maybe this is connected to another computer and we could go in with our scan tool and see a request. Yes, it wants it to roll down. Okay, we're seeing that on our PID. Then inside of the door panel, I would check to see, well, let's see if I can just disconnect this connector from the computer, and I'll put power and ground. Did it go up or down? No. Well, maybe that's because it's all the way up or all the way down, so I just tried to roll it all the way up. It's all the way up. I didn't know, so I'll reverse my polarity. So then I put ground and power. Oh, now it moves. I've just proven that my wires are good, my motor's good, and even that my input was good because I had looked at this with a scan tool to see if I was getting the input. So maybe one of the drivers, one of the little transistors built into the computer itself is burned up. Well, then computer time, we actually get to replace it. They just want you to limit everything down and prove that everything except for the computer is good. And at that point, they say, okay, put a computer in it. They don't actually tell you how to go in and diagnose the computer. Here is a look at what we're going to be doing next week, and I kind of allude to some of this stuff in the lab for this week, but everything on our car is actually built to run off 14 volts. This is everything except for the internals of computers. The reason that everything's built to run off 14 volts is because that's what our charging system's going to average out at, is just around 14. It might go down on new vehicles as low as battery voltage and then all the way up to 15.5, but if I average out the voltage that this charging system is at over like a drive cycle, so the amount of time that I'm out driving the vehicle, it's not going to stay at either battery voltage or 15.5 volts the whole time. It would average somewhere around that 14 volts, so they build the circuits to be able to handle that. Oftentimes we'll have a voltage regulator inside of our module that steps that DC voltage down to 5 volts. This is a clean 5 volts. This thing is varying all over the place. I turn the key on, the engine's off, we have battery voltage. I start the engine up, it jumps up to 14.5 volts. I'm driving around, it goes down, it comes up, it goes down, it comes up. This doesn't matter if I have 12 volts here, doesn't matter if I have 15 volts here. What's going to come out is 5 volts. This is called reference voltage. Reference voltage, 5 volts. And what this does is this will supply a clean voltage to my sensors so that as I get a varying voltage back, right, this wiper would be dropping voltage, so I'd have 5, 4.5, 4, 3.5, 3, 2.5, 2, 1.5, 1, 0. So as that wiper moves back and forth, and I get the signal to this integrated circuit on the inside, then I would know that 1.5 volts means that I'm at, let's call it 15% throttle, and it means always 15%. It doesn't mean anywhere from 10 to 20%. No, it means exactly 15%, and that's huge. It's very, very important. Here is a NPN transistor controlling a relay, which you should do in this week's lab, so you'll understand how that all works. And this, like the lab talks about, allows me to take 5 amps and control somewhere up to the realm of maybe, not 5 amps, 0.005 amps, and control all the way up to the realm of fuel pump motor. This could be turning 10, 15, even 20 amps, depending on the vehicle that it's built into. And it also makes it so that we can very quickly control this relay to be on or off and allow for a returnless fuel system. So we can very quickly turn that on and off. We have a computer making some nice decisions about what the fuel pressure should be, and we don't even need a fuel pressure sensor to be able to figure that out. It just looks off of accelerator pedal and throttle angle, and it can figure out, well, the throttle's wide open, I need the pump to be spinning all the time, or, well, we're just kind of cruising down a hill, so I can duty cycle this pump motor so that the motor's spinning at 25% of its top speed. Diodes are used to gobble up voltage, and I think we talked about this last week with diodes, where when we open up a coil, like inside of our relays, then high voltage, high back EMF or back voltage is created, which could go and fry one of our transistors, and so they put the diode in there so the resistance of the coil just drops all that voltage. There's one on a relay, there's one on a clutch coil for the AC compressor, another fuel pump motor looking thing. And it's kind of interesting where they drew that a little bit wrong, but what are you going to do? Duty cycle. So duty cycle is an interesting one. There are a few different topics that come up, and when we're in the classroom and actually dealing with this, I really harp on it a whole bunch, but it's kind of hard to do remotely. So I'm going to talk about it now, and hopefully you all watch this and get an idea of what I'm talking about. But we have a couple different ideas. I've got Hertz rate, or RPM, which is cycles per second or cycles per minute. Hertz is cycles per second, RPM cycles per minute, right? Revolution, cycle per minute. So that's just how many times something turns on and off over a given fixed period of time. Is it over a second or is it over a minute? Most of our electronic stuff is really worrying about per second because it can think really fast. When we get into duty cycle, what that means is, let's say this wave, see how my on total one cycle is the same regardless, right? So hertz, that's one cycle per whatever percentage of a second. The number of times this happens would actually give me my hertz rate. So like in the wall, our AC current, alternating current, has a hertz rate of 60. It cycles from positive to negative to positive to negative to positive to negative. It does that 60 times a second, so 60 hertz. On this instance, we're not given the time frame, we're not given the hertz rate because it doesn't really matter. It's got a cycle, and if I had 100% duty cycle, that would just mean I had a straight line of power, so it was just on all the way. As I would slow the motor down, or in the case of this image here, dim the bulb down, that's 100. 75, 50, 25, 15, right? It never got to 0 because it didn't turn all the way off. So what we would have is, this is cycling, but the percentage of on versus off will be greater as that light bulb is brighter, and as it dims down, we'll get closer to 50, and then eventually to 25, 15, and if it turned off, we'd have a duty cycle of 0%. What it's saying is, out of one cycle, what percentage is this component turned on for? So duty cycle will be given to us as a percentage. And then the last topic I want to talk about is pulse width, which is often referred to when dealing with engine performance, where the pulse width of our fuel injector is 1 millisecond, so 0.001 seconds, while the vehicle's just sitting there idling. The pulse width is just, there's no consistent hertz rate, right? There's not a consistent sitting there because the engine's going to change speeds all the time, so the cycles are going to change with the speed of the engine. So what they care about is how long is the fuel injector on for. That's pulse width. How much time was it on for? Okay, so a very, very crash course in hertz, duty cycle, and pulse width. So you're welcome. Here is an output side of a headlamp circuit, and these would either have little relays built in, or these would be PNP transistors sending power down to the bulbs to turn them on, because this is power side controlled. You can see the ground down there on the bottom. And then here's our high beam relay. So our high beams are using enough current that our little microprocessor can't quite handle it. And all the microprocessor is doing is using an NPN transistor to ground out this relay and allowing a much higher current, in this case 15 amps, to flow. So this could be, like I said again, it could be 5 milliamps, 0.005 amps, is controlling somewhere in the realm of a few hundred amps, or a few hundred milliamps, so like a tenth of an amp through that coil. That's controlling 15 amps. So we're amplifying the amount of current that this module can control. And this relay is non-serviceable. So if this went bad and we couldn't hear it click when we tried to turn the high beams on and they didn't turn on, time to put a whole body control module in this guy. Here's a look at a GM diagram. And on the top of this, they're showing switches, but this is just to make it simpler for their techs to understand that these lights are being controlled by transistors. They're just visualizing it as switches because, you know, when it comes to brass tacks, that's basically the same thing that's happening on our end of the spectrum. And then these little arrows there are showing that there is a meter inside this module paying attention to whether or not there's voltage here. When this tail light is turned off, then it's not going to have any voltage because it's not connected to power. When it's turned on, we'll see voltage there because we're on the power side of it. It hasn't dropped any of that voltage yet. This allows this module to create codes. So if I hit the brake pedal, the module gets the input that the brake pedal has been depressed. It's going to then try to output to my stop lamps, and it sees that this stop lamp here on pin 1 of the connector going into the body control module, sorry to move you around so much, it sees that this doesn't change state from 0 to 12 or 14 depending on how this is controlled, and it can actually set either a code or maybe the dummy light on the dashboard comes up and says that you have a tail light out, because it's kind of hard to tell if you have a tail light out because you're not really looking that way. So this is how the computer can monitor itself. This is how codes can be generated, and we're going to get into that kind of stuff next week, which I hope you're excited for. Here's a communication network. That communication network is like Morse code between all the different modules inside the vehicle, and we'll go into real depth as far as that goes. But the thing that is sitting there, tapping, closing the circuit, creating voltage and cutting off voltage, that's transistors. So an output could even be how one module talks to another module, right? An input could be message received from another module. So a little food for thought for you. Hope you have a nice week.